So today we're going to talk about Chapter 5, Data Organization and Descriptive Statistics. So far we've been talking about various aspects of study designs. Now we're going to start diving into the world of actually describing behavior using statistics. So brace yourself, statistics is coming, but we're going to baby step into it, so hopefully you don't find yourself super overwhelmed and you'll be a pro before you know it. So, how does your book define descriptive statistics, and what do they tell us about our scores? Well, the book defines them as numerical measures describing distribution of scores. Now, what do I mean when I say scores? Well, think about all the types of measures and ways of collecting data that we've discussed so far. Every observation that we make is considered a score, and descriptives tell us how those scores look. So here's an example. Imagine that we've given a memory test to a group of participants. We have all their scores, but we don't talk about individual scores, right? We talk about them as a whole. If we want to see how well our participants did overall, we would look at the distribution of their scores, right? So descriptive statistics allow us to draw meaning from our data's distribution. This can be done with the center of the distribution, the spread of the distribution, and the shape of the distribution. So why is it important to know your data's central tendency? Well, the book defines it as a representative number that characterizes the middleness, that's tricky to say, of the entire data set, right? So why is that important? Well, when we talk about research, again, we don't talk about each person's individual score. We talk about the data as a whole, right? Representative of our entire sample. So we need to be able to define our data, describe it, and central tendency is one of the ways that we can do this. We can identify a single score that represents our entire group or sample. There are three types, which I'm sure you're all a little familiar with: mean, median, and mode. And the somewhat tricky thing about central tendency is that there's no silver bullet or one-size-fits-all measure that you should always use. What measure of central tendency we use depends on other aspects of our data. And the biggest thing that central tendency can help us with is comparing individuals or groups using single numbers or scores. So, like I said, we have to consider a couple things when we're choosing a measure of central tendency. What scale of measurement are you using? Why is that important? Well, a ratio scale has a 0 to 100 distribution is going to look very different from a nominal scale that represents, say, 3 political parties, right? So we're going to take a look at how the three measures of central tendency individually impact how we can better understand our data and use of statistics. And we're going to start with the mode. So our book defines the mode as a measure of central tendency, the score in a distribution that occurs with the greatest frequency. So put simply, the mode is the one that occurs the most. It's typically used on a nominal scale of measurement, and it has identity, but that's really it. So think about something like your soft drink preference: Pepsi, Coke, 7-Up, Mountain Dew, Sprite, other categories. You could assign a number to each one of these categories, and really it gives them identity, but nothing else. So let's do a practice problem. I want you to go through these numbers and figure out which number occurs the most. Is it 0? Is it 1, 2, 3, or 4? So take just a second, go through, count those numbers, and see which one occurs the most. All right, so based on your calculations, you should see that the number 2 occurs the most. It occurs 6 times in comparison to the other numbers. So the mode for this data set is 2. Pretty simple, right? All right, so do we see any problems with using the mode? Let's think about how the mode may or may not be the best representation of our data. So first, you may have more than one mode. Let's look at this example. So here we have two 14s, two 15s, two 16s, two 17s, and two 19s, right? So in this example, we have 4 modes, and that's really confusing and doesn't tell us a lot about our data, right? And especially it isn't helpful when we're trying to determine the center of our data. So second, using the mode could result in ignoring most of the data, right? So in this example, we'll see that 6 is our mode. However, that's really not a strong representation of the middle of our data set, right? We've got 6, 17, 18, 19, 21, 22, 23. So if we say that the mode is our measure of central tendency here, does that really represent all of our scores? So that's going to bring us to the median. Our textbook defines the median as the measure of central tendency, and it's the middle score in the distribution after all the scores have been arranged from highest to lowest. So, put simply, the median is the middle. It's the midpoint of our data's distribution. 50% of the scores fall above it and 50% below it. And the median can be used with ordinal, interval, or ratio scales. So calculating the median is very simple, just like calculating the mode. If you have an odd number of data points, then you arrange them smallest to largest and find the number exactly in the middle. So for example, the numbers 1 through 7, your median is going to be 4. Now, if you have a number of scores that's even, you're still going to arrange them from smallest to largest. However, when you get to the middle, you need to average your 2 scores. So in this case, we have 4 and 5. 4 plus 5 is 9. Divide that by 2, and your median here is 4.5. So let's practice. This is the same data set we used earlier, so I'm going to give you a second to arrange these numbers in order from highest to lowest. Make sure you're double checking your work and determine what our median is here. Okay, if you need a little more time, you can pause the video. But in this situation, our median or our middle number is 2. So when do we use the median? Now, I'm not going to go into too much detail on why this is preferred with highly skewed data. We'll get to that momentarily. We haven't talked about what skewed data means yet, but simply imagine that our data is not normal. It's being pulled a certain way by a cluster of scores. The median isn't affected by this pull and can still represent the sample. So let's take a look at this example. So here we're going to work with salary frequency, okay? So the mean is the average. Just trust me on this. I did the math so you don't have to yet. And here the mean is $43,500. But the median is $25,000. So see how most of these scores fall between $15,000 and $29,000, but one whopping score of $150,000 really affects our mean. So that one crazy high salary affects our mean, but not really our median. So in here, the median and the mode are the exact same as well. So we can say that 25,000 as the mode or the median of our data speaks to its central tendency better than, say, the mean in this situation. But what about issues using the median? So again, we have the issue of count. It's not really including all the data, just what's physically in the middle. So for set A, we have a range of 1 to 22, and set B is 12 to 22, which means they are quite different, right? However, both data sets have the exact same median, right? If you add together 15 and 17, divide by 2, you'll get 16. So they have the same median even though the values are quite different in these two data sets. And that's going to bring us back to our mean. So how does our textbook define the mean? Well, very simply, measure of central tendency, and it's the arithmetic average. So this is the most commonly used measure of central tendency. It's the exact mathematical center of your distribution. Think of it as the balancing point of your distribution. So here is our first formula of the semester. Don't let it sense your fear. And I'll say this a million times in this class just to kind of ease your anxiety about formulas. You'll never have to memorize them in this class. I will make sure to give you formulas for all your exams, for your practice problems, your labs, anything that you need to do that requires formulas, they will be provided for you. However, you will need to know how to break down and use these formulas. So let's break it down and take a look. So X bar, the first symbol that we see, is what we use when we're reporting the mean of a sample. So if you see X bar, we're talking about the mean. Now the big Greek letter E represents the symbol for the sum of. X represents the individual scores, and N represents the number of scores in the distribution. Now, you will see the Greek letter mu used when reporting the mean for an entire population, but we'll get to that momentarily. So, calculating the mean is simply adding all of the scores together and dividing them by n, so the total number of scores that they are. So let's go back to our how many pets do you have data set that we've done our mode and median with. So take a second and I want you to add together all of these scores, okay? All right, pause the video if you need to, but you should have gotten a sum of 37. If you divide 37 by n, which in this case is 17, you'll get a value of 2.18. And in this class, always round to 2 decimal places. I think it was something like 2.176 or something like that. So we would say 2.18 for this class. All right, so we're going to try another example. These are average commute times on Poplar Avenue in a given week, which anyone who's driven on Poplar Avenue knows that it can vary tremendously. So take a second, add together all of these scores and divide by the total number of scores, and let's see if you can calculate the mean. All right, so you should have gotten a mean here of 21. And 21 is pretty representative of the middle of these scores, right? Wouldn't you say that's pretty average if you look at the difference between 17 and 24? 21 minutes is pretty average for this data set. Now we're going to talk about the pros and the cons of the mean. So we typically use the mean with interval and ratio scales. And it typically summarizes your data pretty accurately because it takes into account all of the scores. So with the median and the mode, we're looking at what? 1 or 2 numbers to try to describe an entire data set. But with the mean, you use all your data to calculate an average score. However, that's exactly the drawback of using the mean. A few extreme scores can pull the mean and make it less representative of the center of your distribution. So let's take a look at this and see if it helps make any sense of what I mean when I say we have a skewed distribution. So first, let's think about the fact that most of our data is not going to be normal, right? It's not going to give you that perfect bell curve. The perfect bell curve is like a unicorn in real statistics. We use it to teach because it provides the clearest explanation of related concepts, but think about human behavior. Is it ever really normal? Absolutely not, especially when we're studying constructs like anxiety, stress, depression. So now we're talking about data that is non-normal in terms of distribution. So our textbook defines skewness as simply lopsided. See how the image on the left is being pulled to the left? The tail is pointed to the left. That indicates a negative skew in our data. On the right, we see the opposite. The pull is to the right, which indicates a positive skew in our data. Do you see how our measures of central tendency are affected by this? With your middle perfect bell curve, they all line up on top of each other, your mean, median, and mode. But for the skewed distributions, they are much more variable, right? This is why we have to be cautious and really think through our measures of central tendency when we're looking to describe our data. And this brings us to measures of variability. So the central tendency measures tell us about the middleness of our data, but not a lot about the variation of our scores. And that single score doesn't really tell us much else. So we need to know how the scores in a distribution are clustered together or spread out. This gives us a more complete look at our data. And we always want to describe our data in as much detail as possible. So let's take a look at this again. We're talking about descriptive statistics here, and we've talked about the far left, the center of our data. Now we're going to be talking about the image in the middle, the spread of our data. And we're going to start by talking about the range. So what is the range? The range is the difference between your highest and lowest numbers in your data set. You will only use those two scores and everything else gets ignored. So let's take a look at two data sets. The lowest score for both of these data sets is 1, and the highest score is 10. So we have a range of 9 for both of these data sets, even though they look pretty different, right? So can you think of any issues with using only the range? Well, the range is easily distorted by an unusually high or unusually low score. We like to know the range in combination with other statistics, like the mean, just to give a better idea of our data. And that brings us to our next concept, the standard deviation. So our textbook defines standard deviation as a measure of variation or variability, and it is the average difference between the scores in a distribution and the mean or the central point of the distribution. So the standard deviation is our most commonly used measure of variability. Most of the time when you read the results section of a journal article, you'll see the standard deviation. Every set of results typically starts by saying, here's the mean, here's the standard deviation of the data, because it gives a pretty clear picture or the gist of the data up front. And then you move on to describing the range, the mode, the median. And this is used with interval and ratio data because it has equal unit size. Now, this is how we calculate the standard deviation for a population. Do we ever really compute stats on an entire population, though? No, we use our sample to generalize to the population. But we're going to talk about that more in just a second. So here you would subtract the mean from each score, square each result, sum the squared deviations, divide the number of scores, and take the square root of that value, which is an important step that a lot of us forget, myself included. So we use our sample's standard deviation to estimate population. Now, a sample of people tends to have less variability than a population of people. So if you're looking at 200 people, you'll have less variability than if you're looking at, say, 2 million people, right? And like I said, we'll be calculating the standard deviation for our sample, which is slightly different than for the population, but it's still important to talk about. So let's imagine this is our entire population's distribution. We've just gotten data from everybody. And the X's are the sample that we take from the population. And you can see by the dotted lines how the population has way more variability than our sample, right? So that brings us to our formula for standard deviation for a sample. So again, this will always be provided for you, and we're just going to talk about this step by step, and then we'll work through actually calculating it. So the first thing you're going to do is calculate your mean, which you already know how to do, X bar. Then you're going to subtract that from each score. Then you will square each deviation score, sum all of the squared deviations, and divide by the number of scores minus 1, which is your unbiased estimator. And then finally, take the square root of that value. Now, before we get into working the formula, let's talk about why we use n minus 1. Samples tend to underestimate how variable the population is, right? We talked about that. The population has more variability than our sample. N minus 1 allows us to account for this by making our denominator smaller and our variability score larger. It kind of helps us fix the underestimation of the sample. So again, let's think about this with this image. You see how the sample variability is much smaller than the population by the dotted lines. N minus 1 helps us to account for all the variability between the population and the sample. So again, I will give you the formula for the exam, but you will need to know why each step is conceptually important and how to use it. All right, so the first thing we're going to do is calculate the standard deviation for the following interest rating data. So I want you to write down each one of these numbers: 3, 8, 5, 7, 6, 5, 7, 8, and 6. Then you're going to subtract your mean after you calculate it, of course, because I'm not going to give you that. After you have calculated your mean, you're going to subtract it from each one of those numbers and then square that value. After you've done that for each one of those numbers, sum them together. So add up all those numbers from when you squared the difference. Then subtract that by n minus 1. And your n here is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? Am I counting that correctly? 1, 2, 3, 4, 5, 6, 7, 8, 9. So n here is 9 minus 1. So divide that sum by 8 and then square root it. All right? Take a second, work this out, and let's see what value you get. Okay, and just for time's sake, go ahead and pause the video if you're not done yet, which I don't expect you to be. But the standard deviation here is going to be 1.62. If you didn't get that value, then pause the video, go through and rework each one of these steps. And we're going to do another practice example just to be safe. All right, so now we're going to calculate the standard deviation for the following final exam scores. All right, let's take a look at it. Go through, subtract your mean once you've calculated it from each one of these numbers, square that difference, sum the different scores together, and then divide by n minus 1. And in this case, we have 5 exam scores, so your n minus 1 is 4. And don't forget to square root there at the end. All right, let's see what we've got here. Our standard deviation here is 9.14. So this tells us that our exam scores tend to vary by about 9.14, which is pretty representative of our data, right? It gives you a better picture of how much your data actually varies. Now I've got a little trick for remembering some of the concepts that we've learned today. It's something that I learned in the 4th grade, and it got me through this class when I was an undergrad, and it's something that I still use today, hence it's in your lecture. So everyone knows the nursery rhyme, "Hey diddle diddle, the cat and the fiddle." Well, there's a song version of that that can help you remember some of the concepts we learned today. So hey diddle diddle, the median is in the middle. You add and divide for the mean. The mode is the one that occurs the most, and the range is the difference between. So memorize that if you want to, laugh at me if you want to. That's just one of the ways that you can remember some of the concepts we've talked about today. Now, we've talked about the center of our data and our spread. So now we need to talk about the shape of our data, okay? So we've touched on a few of these concepts very lightly, but we're really going to dig into them now, and hopefully all of these floating parts start to come together when we're looking at describing our data. So why is it important to know about the shape of our distribution, and what do the different shapes reflect? Well, shape is a good indication of how normal our data is. And we've talked about a normal distribution. This is a normal distribution, a normal bell curve, which is, like we said, a unicorn. You never see this with data. And here's a bad stats joke just to get you through the last leg of this lecture. Okay, so a normal distribution is technically a theoretical construct. We use this normal distribution as a comparison for our data to see how well our data fits the normal curve. And there are a few properties associated with the normal distribution, right? It's bell-shaped, it's symmetrical, the mean, median, and mode are all equal, the distance from each score of the mean is normal, and we're able to calculate percentages based on proportions. So let's look at that. So here you see the standard deviations are under that bell curve. And if we have our standard deviation sat at 0, that shows that our mean, median, and mode are all equal. You can see the distribution on the positive and the negative side of the standard deviations, and we'll talk about the associated percentages a little bit more as well. But see, one standard deviation in a positive direction and one standard deviation in a negative direction are equal, right? So we've got an equally divided bell curve here, which is important. So we've talked about positive and negative skewed data just a little, but skewed data simply means that it's lopsided or not normal. And most of our data is going to be skewed in some way. So this is my favorite image comparing all three distribution types. We looked at it a little bit earlier. And you can see how the data is being pulled in one direction, which skews our data and also impacts our measures of central tendency. So the normal bell curve in the middle, again, mean, median, and mode are all stacked right on top of each other. But A, the negatively skewed model, shows that the mean, median, and mode get pulled apart and represent different points in the data set. And same thing with image C, the positively skewed data set. If that data gets pulled in a positive direction, you see that the mode, median, and mean are once again pulled to different parts of that distribution. They're no longer representative of the exact center. So with a positively skewed distribution, the peak of our data is to the left and the tail is being pulled towards the positive end of the number line. And why does this pull occur? Well, extreme scores, right? So think back to our salary example. That $150,000 salary may be pulling our data in that positive direction. Now with our negatively skewed distribution, we see our peak is to the right, or the center is to the right of the center data point, and the tail extends to the negative end of the number line. So these extremely high negative scores will pull the mean towards them. And this brings us to kurtosis. So what is kurtosis and why is it important? Well, we've talked about the shape of our distribution in terms of skewness, or which direction the data is being pulled, but now we want to look at another way we can describe the shape of our distribution. So kurtosis, as defined by your textbook, is how flat or how peaked your distribution is. So I'm going to show my age a little bit here. I like to use the movie Twins with Danny DeVito and Arnold Schwarzenegger to kind of describe your kurtosis. So kurtosis is simply how flat or how peaked your data is. And this is a continuum. So you can have like slightly kurtotic data or really kurtotic data. And again, the Twins movie is a good way to think about this. So for leptokurtic curves and leptokurtic distributions, a few of the scores in the middle have high frequencies, which result in a peak that makes our distribution taller and more thin than a normal distribution. Now, the opposite of this is a platykurtic distribution, which occurs when most of the scores in the middle have similar frequencies, which results in our distribution being shorter and flatter than a normal distribution. So here I like to think of the leptokurtic as Arnold, tall and thin, and Danny DeVito as more shorter and, flatter, if you will, to be kind. All right, so just to do a little practice with our skewness and kurtosis, let's look at these example distributions of exam scores for different sections of classes and talk about how they look. So for section A, we would call that a negative skew. As you can see, the tail is being pulled in the negative direction. For section B, we have a positive skew, right? That tail is being pulled more towards that positive higher end of your number scale. For section C, we see a pretty normal distribution, right? That's about as normal as it gets. Now for section D, we see a platykurtic distribution. See how flat all of those scores are? Section E, we have a leptokurtic distribution, so super peaked and super pointed at the top. And section F is something that we call a bimodal distribution, right? So bimodal because it's got two modes, two very frequent kind of humps in your bell curve there. Now, in the real world, we typically have to transform data to normalize it before we can compute statistics. And I just wanted to give you a visualization of what this looks like so that if you ever come across it, you'll kind of understand what's going on. So we're not doing this in class, but again, I just want you to visually understand what's going on when you do encounter these types of things doing statistics in the future. So as you can see, we have a positive skew at the top, right? See how those scores are pulled towards the positive end of our number scale. Now, once the distribution has been transformed, it's more normalized and it forms a better fit with a normal curve, right? So that makes our statistics a little bit more appropriate. And you can see the same thing with the bottom example as well, right? So that's more of a negative skew. I don't know, that one can be a little tricky because it does look a little bit more negatively skewed to me. And after we transform that data, you can see that it falls along the more normal bell curve. Now, the last thing that we're going to talk about in this lecture are z-scores. So how are z-scores defined in your textbook? Well, z-scores are information about a single score relative to all other scores in the sample or population. Now, z-scores are appropriate only for interval or ratio data, right? You can't use nominal or ordinal data for these. Now, specifically, z-scores tell us how many standard deviations an individual is from the mean of a distribution. So whether someone falls above or below the mean. And we do this so we can actually talk about our data. So this translates our raw scores into more common language so that we can make comparisons. So for ACT or SAT scores, who can tell me what the ranges are or the means? So how would we compare here, right? How would you compare your ACT or SAT score with someone else or with each other? So here's the formula for a z-score for a sample. Again, you will not have to memorize this. It will be provided for you, but you will have to know how to use it. So to obtain z, we have to subtract the mean from each value in the data set and divide by the standard deviation, right? So the x reflects each value in the data set. The x bar reflects the mean, which you already know, and s reflects the standard deviation of the sample. So let's work an example. Here we have interest ratings again. So in this example, I give you your mean and your standard deviation. So for person number 1, if they had an interest rating of 8, what is their z-score? And what does that tell us? Well, you're going to take their score of 8 and subtract out 6.11, right? And that's going to give us 1.89. Then you're going to divide that by 1.62, your standard deviation, and that's going to give us a z-score of 1.16. So this person is about 1 standard deviation above the mean. So I want you to try to work the next one on your own. So if a person had an interest rating of 3, what is their z-score? So take their z-score, subtract the mean, divide that by the standard deviation, and what do you get? Well, you should have gotten negative 1.92. So 3 minus 6.11 equals negative 3.11 divided by our standard deviation of 1.62 gives us a negative 1.92 z-score. And that means that this person is almost 2 standard deviations below the mean, right? That's what that negative value tells us. All right, so if we based our understandings of our data on the standard bell curve, then the area under the curve gives us information on how scores are proportioned in our distribution. And this is really important when it comes to z-scores. So do you see how the percentages that are under the curve are associated with the standard deviations? Well, this will make a little bit more sense momentarily, but again, I want you to understand what I mean when I talk about under the curve, right? Those standard deviations and their cumulative percentages. And see how with 0 in the middle, if you move to the right, you see your positive values. If you move to the left, you see the negative values. Probability is the expected relative frequency of a particular outcome. With our distributions, we know the exact proportion of scores that fall between the mean and a z-score. We also know the proportion of the scores beyond a z-score. And why is that helpful? Well, we can determine how likely we are to get a certain score or how unlikely we are to get a certain score. And that's what you'll do with your practice problems this week. All right, so I wanted to walk you guys through this. So first you'll need to find the absolute value of your z-score, right? So if you have a z-score of negative 1.35, then you're just going to use the absolute value of 1.35 here. So we don't have any negatives here. We don't use those when we're using the table in the back of the book. So let's say that someone had a z-score of 1.36, right? And we want to know what's the probability that that person scored higher than the rest of the class or that someone scored higher than her. Well, first we're going to find 1.36 in that far left-hand column. And then we're going to look all the way to the right in the area beyond the z column. And as you can see here, that score is equivalent to 0.08691, and we rounded 2 decimal places in this class. So that gives us a probability value of 0.09. So the probability that someone scored better than the student we're referring to would be 0.09, right? All right, let's try another one. So there's some probability practice problems on table A2, page 429 in your textbook. You can go ahead and pause the video, get that all pulled up. But what is the probability that someone scored better than our friend Tegan here, who got an ACT z-score of 1.80? Well, I'm going to give you just a second to work that problem out. Pause the video if you need to. All right, so if you use the table in the back of the book, you'll find the corresponding probability value here is p equals 0.04. So the probability that someone scored higher than Tegan is pretty low, right? She did pretty great, or they did pretty great. Now, who can tell me the probability that someone scored worse than Cal? Well, Cal has a physics final z-score of -1. And what is the probability that someone scored worse than Cal? We'll take a second, pull up the table in the back of your book, and let's see what the associated probability value is. You should find that the associated probability value with a negative z-score of 1, and remember you're going to look at the absolute value of that z-score, is going to be 0.16. So it's not very likely that someone scored worse than Cal, right? He kind of bombed his physics final. So I want you to take a second, go back through this video and anywhere that you're struggling, go through your practice problems and your lab assignment for this week. If you have any issues, make sure that you're reaching out to me or even contacting the tutoring center. I posted that announcement last week on our announcements page. There's a flyer for contact information on helping with statistics tutoring. But please don't be confused. If you are confused, reach out, all right? Ask questions. Let's get you to a place of understanding before we move forward any farther. So that is it for Chapter 5, Descriptive Statistics.